Section 9.2 is all about gas laws, so the equations that we use to describe gases. Ultimately, they're all going to boil down to the combined gas law and the ideal gas law. So these may be familiar friends to some of you, but first we're going to talk about how they came to be discovered. So, empiricism was born in the 16th century. Francis Bacon wrote about how we can actually record observations of things and make sure we know, like, things are repeatable in nature. So science is really sort of born at the cusp of the Enlightenment. But really, all that we had to go on, all that scientists in those times between the 16 and 1800s had, were repeated observations and trying to make relationships between things clear by repeated experimentation. And so all the gas laws come out of that kind of sledgehammer approach to science. It's not very fine-tuned, but it is profound, what they were able to come up with. So all these laws are named after people. You don't have to memorize which is which, but do make sure you understand whether things are proportional or inversely proportional, in particular where things come from. So Boyle developed an experiment where he increased the pressure of something and then watched what happened to its volume. This is easily done with a piston where you compress a gas, and so you decrease the volume, see the increase in pressure. But what we want is a graph that we can make sense of. So curves usually are not very helpful. They didn't have computers or calculators to do best fits or anything like that. And so what Boyle found was, by studying the graphs, this is all at a constant temperature, by the way, if he took the inverse of pressure, he got a straight line. And so y equals mx, we have a line here. Sorry for the kaleidoscope effect. The slides got a little jumbled. But what he found is that pressure and volume are inversely proportional in a linear fashion. And so if we made that equation of a line, y, 1 over p is y, equals mx, where m is some constant k. So the slope of this line is represented by that green k. So all of this is at constant pressure, temperature, and in a sealed container, so no gas can leave or come into the experiment. So here's our equation of the line. The way that we write this relationship is volume is proportional to 1 over p. So this is an alpha, Greek letter lowercase alpha, and it's used to say is proportional to, or is proportional to. Alright, so 1 over p equals kV. We can rearrange that so that PV equals 1 over k. So multiply both sides by p and divide both sides by k, do some algebra. That's just another way of saying that PV is equal to some constant. If that constant is the inverse of the green k, it doesn't matter. I'm just accounting for PV equaling some consistent number. But this will be the inverse of the slope of the empirical data. But because now that both pressure and volume are in the numerator, we'll use this kind of form of it going forward with the green, bluish K. Alright, so Boyle's law is particularly useful when we have two different samples or we change the conditions that the gas is under. Both of these gas samples have some volume and some pressure, and both of them relate to each other, pressure versus volume, by that constant K. And you can kind of see, oh, the higher the volume, the lower the pressure. The system has kind of relaxed a bit. There's more space between these balls. They're not going to collide with the container as much. Whereas in the second condition, we've decreased the volume, but significantly increased the pressure because we're going to get more collisions, more force over a little bit smaller area. And so because we can set both of these conditions equal to the same constant, what we get out of that is the transitive property of mathematics. So A is equal to B is equal to C means that A is equal to C. And we get this equation, P1 V1 equals P2 V2, and that is Boyle's law. But remember, in 9.1, we talked about 4 different variables that we can use to describe a gas sample. So we need to be able to describe some of those other things. So Charles's law compares volume to temperature. So if you want to challenge yourself a little bit, look at this data and look at the graph and decide whether you think volume and temperature are directly proportional or indirectly proportional. So directly proportional means that as volume increases, temperature would also increase. Indirectly proportional would be where one increases while the other decreases. And what we see is that volume and temperature are directly proportional. So this line is linear without having to take the inverse of either variable. Volume and temperature are directly proportional. The way that we write that out symbolically is with that alpha in between. So volume is proportional to temperature. As you raise the temperature of a gas, you'll also increase its volume. Sorry, my voice is catching a lot because I had some dairy, but yeah, you didn't need to know that. But anyways, so the way to describe this line, y equals mx, b is 0, that y-intercept, y equals mx. I've colored the k yellowish orange in this one, just to distinguish it as being a different k. So this constant isn't necessarily the same as the constant in Boyle's law. We can also relate two different conditions of gases or change something. So let's say we have a gas at a low temperature and then we heat it up and increase the temperature. What we'll see is that the volume also increases. The other thing to note is that when we actually solve this out to equal k, we have to put V1 over V2. And so we get the same kind of mathematical form where we have V1 over T1 is equal to k, and V2 over T2 is equal to k. If they're both equal to that same thing, then they're equal to each other. V1 over T1 equals V2 over T2. And so that is Charles's law in mathematical form. We would use it if we're given 3 variables to solve for the 4th. One of the kind of interesting results of Charles's law is that scientists extrapolated down the temperature scale and discovered absolute zero as a concept this way. So it's defined as negative 273.15 degrees Celsius. That's because the Celsius scale is already in place. Celsius is based off of the properties of water. So at 1 atmosphere, water melts or freezes at 0 degrees Celsius and boils at 100 degrees Celsius. And so that's why it's like an odd number, 273.15, that we use for these conversions, is because, well, Celsius was already around, and so they just found the solution to absolute zero from that point. The other thing is that it doesn't matter how much of the gas we have. So here are different hydrogen amounts, different pressures of hydrogen. Here are different kinds of gases, constant moles. All of them extrapolate down to the same theoretical absolute zero. And that's kind of an interesting thing to note too about absolute zero. Well, actually 2 things. The first is that it's theoretical, meaning that it's never been observed in reality because it's almost impossible to reach. To make something so cold it stops all motion and takes up no space. The second thing is that for all of these calculations, we have to use temperature in terms of Kelvin, not degrees Celsius, because it's an absolute scale. So to actually relate these lines to each other, or these lines to each other, I have to have the same starting point for what 0 is. Plugging in 0. Well, let's just think about it. If you divide anything by 0 degrees Celsius, then you'll get a infinite answer. So that won't work so well. So always use Kelvin in this chapter, and generally all the time for calculations when in doubt. Alright, the next gas law is Monton's law. It's also called Gay-Lussac's law in different textbooks. There's some debate on who discovered it first. Monton was earlier, and some of his work has been becoming more clear based on research. So it looks like he might have come up with this pressure-temperature relationship first. So just so you guys know, you might see it under both names. But his experiment involved taking a gas that's in a sealed flask, so volume is constant, moles inside are fixed as well. And he heated it up. So here's a hot plate. Turn it on. Gas inside gets hotter. More collisions occur with the sides, and that causes the pressure to increase. So as you heat up the gas, you'll see the little dial on the pressure goes up. So as one increases, so does the other, which means that these two things are directly proportional. We could take some data. Notice again that we have to convert degrees Celsius to Kelvin. And I'm going to run out of time on this video, so we'll come back in 9.2b.